This section gives a theoretical basis to understand the different security controls available to practitioners and organizations regarding data security. Each of the items listed here will be elaborated on and explained in Part 2. Security requires an organization to implement three components: people, policies, and technology. The people have to be trained and qualified to do the job that they are doing. Policies should prohibit physical security bypasses. For example, an organization could have the best security software, but somebody could take a picture of the screen with a cell phone. Governments have a policy that cameras and cell phones are not allowed when working with classified information. This is a good example of a policy that improves cybersecurity. Technology serves as a way to enforce the policy and aid the people in doing their jobs. The pillars of information security are confidentiality, integrity, availability, and non-repudiation. Confidentiality means that private data is not disclosed to unauthorized parties. It can be violated if an unauthorized party can see data that they were not supposed to see, such as attackers seeing sensitive data following a data breach. Data breaches are generally violations of confidentiality. Integrity is making sure that data is not manipulated by an unauthorized party, and integrity can be violated if an unauthorized party can tamper with the data. For example, a hacker changing the account balances of a bank account in a database or ransomware modifying files by encrypting them would both be violations of data integrity. Availability is making sure that data can be accessed when it is needed. Violations of availability would be if an attacker can cause a file server to crash so that nobody is able to access their files, resulting in unavailability of the files. Non-repudiation means that actions have side effects, such as being audited or logged. It would be violated if an attacker can impersonate someone and perform actions on their behalf or deny having taken an action. Authentication means proving a statement that you make. For example, if you want to log into a system with a certain username, your knowledge of the password proves that you are the user whose account you are trying to log into. The problem with authentication is that the entire authentication process relies on one password, which can be stolen, resulting in a compromise of the whole authentication process. If all security measures depend on just a username and password, as it often does today, the theft of credentials would allow compromise of the whole authentication process. Three common ways to double-check authentication include something that a user has, something that a user knows, or something that the user is. A trusted platform module is a physical chip inside a computer with a unique cryptographic key and identifier burnt into the chip at manufacturing time. Since the TPM chip is already included in the computer itself counts as something the user has without the user having to carry any additional hardware devices. TPM is implicit multi-factor authentication and is very convenient because it requires no change in the behavior of the user. More about TPM chips later. In the mainstream computing industry today, trust is neither provable nor quantifiable. Therefore, it is an invalid premise for any security system to assume the user, device, or network is trustworthy. For example, human employees of an organization might have malicious intent and turn out to be malicious insiders, like Edward Snowden at the US National Security Agency. The insider threat vector is still an unsolved problem in the industry today. Human error by well-intentioned insiders can be just as dangerous and cause a data breach just as big if users accidentally email or upload the wrong data to the wrong place. Computers must be assumed to be compromised because if malware or a zero-day exploit is good, the user would not know about it, by definition. In fact, the line between benign and malicious software is unclear, since software that comes bundled with your operating system can often be used for malicious purposes. A prime example is that PowerShell comes bundled with Windows, but has shown to be usable as an attack tool. Networks also must be assumed to be compromised, and it must be assumed that the adversary has the ability to monitor and manipulate network traffic. The only valid and practical assumption is that neither the user, device, nor the network is trustworthy. A strong approach would assume all three are compromised and go from there. Since software depends on the hardware in order to run, and hardware is executing the software instructions, hardware has a higher level of privilege. If software relies on hardware that it doesn't have the capability to influence the internal invariant mechanisms of, the trust can be rooted in the hardware system. A trusted platform module is a tamper-resistant physical chip inside your computer that holds secret keys. If used, it can ensure that nobody can copy your laptop hard drive and put it into another identical laptop. It has a unique cryptographic key burnt into it at manufacturing time and already comes in commodity laptops, especially enterprise computers from companies like Dell and HP. In fact, your work computer probably already has a TPM chip installed, whether you know it or not. Because most enterprise-grade computers already have TPM chips installed, rooting trust in TPM chips is an ideal way to implement multi-factor authentication along with requiring a username and password. Another benefit of a hardware coprocessor such as a TPM is that its memory is isolated from the main memory, so malware on the computer cannot access the private keys on the TPM chip. If data can be routed to TPM chips, it is possible to lock down files to be openable in a specific enterprise only. We will get to this later. The Intel CPU's VTX instruction set also allows software to root trust in internal hardware isolation mechanisms that the software does not have the capability to influence the internal mechanisms of. Hardware can be more difficult to administer and more expensive if it does not already come pre-installed. Security through isolation is the age-old idea that one should partition their valuable assets away from the public eye. The same idea applies to processing sensitive data. One example of this idea is air-gapped computer networks. Another example of this idea is the Intel VTX instruction set, which allows mutually distrusting virtual machines to isolate their memory from each other, again, using trust rooted in the CPU hardware. Amazon Web Services also uses the Intel VTX isolation mechanism if they were hosting a VM from, let's say, Pepsi and Coca-Cola on the same physical server, where it would be disastrous if Pepsi and Coke could see each other's data. Security through isolation can be seen yet again when looking at TPM chip design. TPM is a separate, discrete coprocessor that does not share sensitive memory with the rest of the computer. All of its sensitive computations are isolated from the main memory of the computer. Again, it is partitioning valuable assets away from the quote-unquote public eye. Steganography is the practice of hiding in plain sight. Let's say, for example, a malicious insider wants to steal a social security number out of the organization. The number is 999-961770. This can be expressed in an infinite number of ways, and two examples are given here. Greatest THR33 digit integer dash number of C3 NTS in a dollar minus 4 dash year the U.S. Declaration of INDA 3 P3ND 3NC3 was signed minus a fuzzy picture. If you think about it, to a human this makes sense. They would be able to decode this and get that social security number out. But there's no way a machine would be able to detect this. You cannot write any signatures for this. Another example is just in a story format. I can see 999 green ducks sitting in a row. 96 of them have extra long beaks. There are 1,770 ducks total in the flock of ducks. This sounds like a story. It could have been what somebody did this weekend. There's no obvious clue that it could be steganography. The point here is that artificial intelligence, natural human intelligence, machine learning, behavior analysis can all be bypassed by steganography because it's impossible to list all the different variations of encoding some data. As a result, it is impossible to detect or train artificial intelligence for all of the different variants of steganography. If there is one way to bypass AI, it would be through steganography. Although the previous slide had an example of steganography through text, steganography does not always have to be through text. In this example, you can see an image on the left side of a tree, but what you cannot see is that there is actually another image embedded inside of it. The cat picture that you see on the right is actually embedded inside of the tree picture. The hidden image of the cat is revealed from the tree by removing all but the two least significant bits of each color component and a following normalization of the image. And the link is on the bottom if you want to know more about how that can be done. An algorithm is a set of well-defined steps to solve a problem. It can be written in software and it can be proven to be 100% correct. An example of an algorithm is, if data is created or modified by an employee of the organization, automatically encrypt it. A heuristic is an educated guess or a rule of thumb. Guesses cover general cases but not exceptions and are not provable. Some examples of heuristics include artificial intelligence, machine learning, and detections. A concrete example of a heuristic is if it's 3 digits followed by a dash, followed by 2 digits, followed by another dash, followed by 4 digits, it's probably a social security number. It's an educated guess, so encrypt it. But as we discussed earlier, steganography can bypass all heuristics. As a result, heuristics really keep the good guys good, but they don't do anything to stop the bad guys. While both heuristics and algorithms have their places, in the information security industry, defenders are competing with intelligent human adversaries at the end of the day who are handling the data, writing the malware, and probing the networks. Humans are smarter than machines and can and do and will continue to be creative to outsmart heuristics using anomalies and steganography. For this reason, it is dangerous to try to use heuristics to compete with intelligent human attackers who are trying to steal data. It is better to use provable algorithms rather than heuristics that can be fooled by attackers, especially in open-ended problems like identify all the possible ways to encode a social security number, as seen in the previous example. Artificial intelligence and machine learning require training sets to learn on. These training sets cannot be exhaustive. For example, they cannot identify all the possible ways of expressing a social security number. Remember, artificial intelligence tools are now being used by both attackers and defenders. Secure by default and insecure by exception is a basic engineering principle for building fault-tolerant systems. It makes it easier to be secure and harder to be insecure, and makes human errors less destructive. For example, a high-power electricity line only has current flowing when the operator presses and holds a button. When the operator lets go, there is no current, rather than the opposite, where the operator has to press the button in order to stop current. In this system, if the operator makes a mistake and does not press a button, there is no catastrophe because there is no current flowing if they don't press the button. Separation of duties requires multiple parties' authorization in order to allow something to happen. This way, if one of the parties mistakenly or purposefully goes rogue and does something bad, the other parties can act as a safeguard from a negative outcome. Change is hard because it requires users to relearn things. It is important to make minimal changes to user experience, otherwise users would do things like disabling security features or complaining to the IT department. For example, people who are not in IT and that don't work with technology all day, such as people maybe in legal or finance, might not learn technological changes as fast. Change is expensive, and people actively avoid replacing their technology if they can. Widely adopted technology is rarely changed, especially if the argument is for more security. History has shown time and time again that the industry is not willing to rebuild technology, especially if the same features will come out of it, just in a more secure manner. The industry would rather build on top of what is already there and fix problems with a patchwork of interoperable band-aids, such as IPsec's band-aid for IPv4's insecurity. The same can be said about complex file formats, applications, and operating systems that have evolved through decades of engineering. An extreme example is if somebody came up with a perfect operating system that had no security vulnerabilities. In order to make it usable, they would first need to build a web browser, and then productivity applications, and then the rest of the ecosystem to match other richer ecosystems that are already out there today. Then they would have to convince everyone to throw away what they are currently using and use the new platform, even though it's a matching feature set, and they don't get any new features out of it. Hypervisors provide an interoperable way to get under the mature operating system and applications for additional security without having to rebuild or rewrite or redesign or re-engineer anything. If we are assuming malicious insiders, compromised devices, and compromised networks, we must also assume that the data has, is, and will continue to be exfiltrated from an organization, in which case encryption and protection should follow the data. This threat model is particularly relevant in today's world of bring your own device and cloud, where data legitimately can end up on the devices and servers of others that the enterprise does not own or control. Full disk encryption allows protection to follow to a limited extent because the protection follows the disk around, but the protection is stripped if the data is shared from the device, such as through email attachments or uploads of files that are on the device's encrypted disk. Security increases as the encryption becomes more granular, from the disk level down to the file or database cell level, because data is encrypted wherever it ends up. In a world where we must assume data exfiltration is occurring, protection should follow the data because we don't know where the data will end up. For example, it can be stored in a cloud provider's server, an adversary's server, or an employee's device. In all cases, it would be protected. Enterprises often want proof that their security is working. This proof can be provided by auditing operations following the concept of non-repudiation discussed earlier. For example, if a user creates, modifies, or shares a file, and the server records analytics about this example event, management can gain confidence and comfort that the security is working only if it can be seen on the management server that this operation occurred. Structured data is machine understandable. It is organized into machine accessible pieces, and this organization allows the data to be algorithmically parsed and, for example, stored in databases. Often you can tell if the data is structured if it is organized into tags, fields, or offsets. Some examples include XML, formatted or delimited text, or file formats. Unstructured data is human understandable. It is ambiguous to computers and disorganized and has unformatted structure. Some examples include human languages, rasterized images, audio, and graphics. In the example here, you can see on the bottom of the screen that the word credit is wavy and has different boldnesses and thicknesses. And this is not a standard and a structured and an organized format. The word credit has one format and the word card number has different formats. And so a human can understand it because it looks like the word credit, but machines have a more difficult time when you're trying to tell it that it looks like something, when you're trying to express that something is similar to something else, but not the same. As security research advances, the industry sees new attacks on cryptographic algorithms. As computers become faster, smaller key sizes lose their security properties, and longer key sizes need to be used. As geopolitical situations arise and evolve, different cryptography standards are approved and rejected by different organizations, and this all evolves over time. This ephemeral cryptography trend should be taken into account when implementing security in systems. Crypto agility expects algorithms to be obsoleted or rejected and key sizes to become too short, and plans pluggable cryptography into systems because of the expectation of evolution of cryptography over time.